The first topic will be fast and exact convex hull simplification. So over to you, Georgie. So it will be 8 minutes of your talk, followed by 4 minutes of Q&A.
Everyone, today I will be presenting the paper The Fast and Exact Convex Hull Simplification. Now I will talk about the problem definitions, and first let CH of P be the convex hull of all points in P, and computing convex hulls is a fundamental problem in computational geometry, and finding subsets to minimize the sum cost function of Q and P is also well studied. So now I will introduce the definition of the cost set we use. So the cost of two sets Q and P is the maximum distance from points in P which are outside the convex hull of Q to the convex hull of Q. And using that cost we can define two versions of the problem where we select the subset Q of the given point set P in the plane. And we are either given a bound on the subset size and we minimize the cost of QP, or we are given the bound on cost of QP and we minimize the subset size. And we call those problems min epsilon and min k versions respectively. And we can also consider the same problems but restrict the given point set P to be in the convex position. And this will give us another two versions of the problem for a total of 4 versions. Now I will briefly mention prior and related work for our problems. For more detailed descriptions, please refer to the paper. So a very similar topic is the core set studies, where the subset is selected such that it preserves some geometry of the given set of points, and there are many results in that field. So another similar topic is where the hull we select is not necessarily a subset of the given points. And also polygonal chain simplification is a very similar topic. Now I want to talk about the intuition for the min-k algorithm for the convex version of the problem. And notice that if we view points as a convex hull, we have a circular ordering of points and we can assign each point that contributes to the cost to some h based on that ordering. And this means that the cost of any hull is the maximum of individual h costs. Also notice that if we fix any vertex and move another one along the circular order, cost would monotonically change. So for the min-k version, we can be greedy and go as far as we want as long as the cost does not exceed some given epsilon. By f epsilon of I, we define the furthest index j such that the cost of the edge ij does not exceed epsilon, and we call that index the friend value of I. Now, if we have a sequence of indices in the circular ordering, at some point they will wrap around from higher to lower indices. So we define a greedy sequence to be such sequence of iterations of f of epsilon such that it goes as far as it can before wrapping around. And we define the greedy sequence to be valid if by applying f epsilon to the last index in the sequence we get a result which is at least as large as the first index in the sequence. And we prove that any valid greedy sequence with a minimum cardinality would be the optimal solution to our problem. If we know all f epsilon values, then to solve the problem we define a directed graph, which is a graph of f epsilon restricted to edges which go from lower to higher indices. So G is a forest such that any path from a vertex to a sink is a greedy sequence. So to solve the problem, first we construct the graph G, then pair vertices to sinks, then remove the pairs which are non-valid sequences, and then out of the rest we find the pairs with the minimum length path to get the solution. And we can do those operations in linear time. So what remains is to compute the f epsilon values for all vertices. To compute the f epsilon values, we use a result from the paper called farthest point queries with geometric and combinatorial constraints. And I will not go into details, but with some additional work we can compute f epsilon values for all vertices in n log squared n time. So overall that would give us n log squared n time for the min-k algorithm for the convex version of the problem. Now, to solve the min epsilon version, notice that we can use the min k version as the black box for binary search if we have a list of candidate epsilon values. And the epsilon values are simply the possible values for h costs, but their amount is quadratic in n. So instead of finding this set exactly, we use a sampling similar to the one shown in the paper called the Frechet distance revisited and extended. If we sample from the set of epsilon values, we may miss the true answer, but we can limit our research range. So if we solve the problem in a sample, we get a range of possible epsilon values. I will not go into details, but we can compute the list of those values, and the running time depends on the number of values we extract. And if our sample size is 4n, then the probability that that size of the list will exceed order of n log n is very small. So to solve the problem, first we do all the required precomputations, then we sample for n values and binary search on that sample. Then we get a range, and after extraction a list of values to search again, and we binary search over that list to get the true answer to our problem. Now, with high probability, the algorithm will run in order of n logged cubed n time, and in the worst case, the running time would be n squared log squared n. Now we talk about the versions of the problem where the points are not required to be in the convex position. And to solve the min k version, we can use an approach similar to the one used in the paper called sparse convex Kuhl average. And essentially, we can convert the problem to the graph problem, where cost of hole is decomposed as the max of h costs, which will be weights for our graph. And all h weights can be pre-computed in n squared log n time. To get the solution for the min k version of the problem for the general case, we just need to find the cycle with minimum cardinality in our graph, such that all edges in that cycle are bounded by epsilon. So by removing all edges with weights larger than epsilon and ignoring weights, we can apply all pairs shortest path as a black box to solve the problem. And running time we get is essentially the running time for all pairs shortest path on directed unweighted graphs. To solve the min epsilon version of the problem for the general case, we binary search over the set of candidate weight values, similar to how we solved the convex case. So we get a quadratic number of possible weights, so we can directly binary search over it. And the running time is essentially the same as the min k running time. And we can also slightly improve the running time if k is small by using a different graph algorithm. Thank you for listening to our presentation.
Thank you, Georgie. Let's speaker.
Thank you.
Do we have any questions in the audience? Okay, so I have a couple of questions. So first of all, I really enjoyed reading the paper. So yeah, it's a very nice argument. So,
Thank you.
So my first question was, can this be extended to 3D? I mean, this problem, how easy or hard is it?
Well, yeah, it would be harder in 3D. So in if you talk about like the one paper I mentioned is a paper where we discussed the different cost function where we have like a sum of squares cost, and we prove certain like hardness results in hard dimensions. So some of them we don't show any hardness results here, but it should be possible to get some version of hardness in 3D. Maybe some like modified problem, but yeah, we expect to be like a much harder version in hard dimension.
You're saying starting from 3D itself, it will be harder.
Well, yeah, and be hard, but maybe not necessarily this version of the problem, because for that other paper we do slightly different version where we do different set of points. So we have a different set of points from which we select from, and the one that we compute the cost from. So this is the one.
Yeah, so, because for example, they're in convex position, right? That's one of your assumptions, right? So then maybe some approximation algorithms, is that possible?
All right, yeah, I guess if we talk about convex positions, then Yeah, something may be possible. Yeah, I guess we haven't really researched in that direction. Yeah, I was talking about like the more general case. Yes.
Yeah, and in general, I mean, one interesting line of work could be this: in the database community, there's a lot of work that's done on skyline points. I mean, computational geometry, we call them maximal points. So there, they look at many such variants where they want to pick only k skyline points, right, which are represented. Right? And they have a lot of applications in the database community. So I guess, given the tools you have, you might be able to extend. So skyline points are easier to handle in higher dimensions as well, unlike convex hulls. So that could potentially be one line of work.
Yeah, okay, thank you, yes. I'll look into that, yes.
Good. So anyone else has any questions, or should we move on to the next talk then? Okay, so let's move on to the next talk then. The next talk is the largest similar copies of convex polygons in polygonal domains. I'm assuming the speaker is Takeng Ho. Yeah, so you have 8 minutes for your talk and 4 minutes for Q&A. Over to you.
I will start presentation. Thank you for introducing me. My research is finding the largest similar copies of convex polygons in polygonal domains. I worked this problem with Seung-Jun Lee and Higap An. Then let's define our problem precisely. Before I define the problem, I will mention convex. Left polygons are convex and right polygons are non-convex. Rights are non-convex because of those pointed parts. And let P be a convex polygon with k vertices, and let Q be a closed region with some obstacles with total and vertices. Then the goal is find the largest polygon similar to P that can be inscribed in Q. In this case, P is allowed translation, scale, and rotation. Then I will mention some preliminaries. In this problem, we define the P distance with convex polygon P as the following equation. In the figure, R is the farthest from P in P distance, and QS have the same P distance from P when large P is a square. P distance defines the H-Voronoi diagram in our problem. From now on, I will abbreviate H-Voronoi diagram to EVD. The EVD subdivides the plane into regions as the right figure. Each side of Q corresponds to a region of EVD, and every square centered in the region touches the corresponding side. For example, the blue square centered in the green region touches the corresponding edge site. When we allow only translation and scaling, P can be the largest in Q when P's center is on the Voronoi vertex as the right figure. For example, the red dashed square is larger than the blue one, but it contains a point of Q in the red square. So blue square can't be enlarged in Q. The Epsilon triangulation is the dual of the EVD. I will abbreviate Epsilon triangulation to EDT. A Voronoi vertex of EVD corresponds to a triangle of EDT. So P is largest when P contains a triangle in the EDT of Q. Each triangle of EDT corresponds to a candidate of largest polygon, so we detect all changes of EDT to find the largest polygon. EDT changes when P rotates as the below figures. In the left figure, two dashed triangles in EDT corresponds to two squares, so the EDT is a rectangle with a diagonal. When P rotates counterclockwise, the red diagonal in the EDT is flipped as the figure. We call this an edge change. The other case is label change. In this case, an edge of P and edge of Q touch each other when P rotates counterclockwise. In the label change, the vertex of P touches with the red edge of Q is changed. We count those two kinds of changes respectively in our research. For finding a largest similar copy of P, the algorithm stores the detected changes in the priority queue. Then, the algorithm updates EDT using the priority queue. While updating and maintaining EDT, the algorithm also finds all candidates of the largest polygon. Q and Kadam solving this problem in this time by bound the number of the combinatorial changes to this time. They used the algorithm in the previous slide. We denote alpine as the inverse Huffman function, which grows extremely slow. Charles and Toledo gave an algorithm for solving this problem using the parametric search technique of Megiddo. Thus, two previous algorithms are not comparable to each other. If n is bigger than k, the algorithm of Chu and Kadam is faster than Charles and Toledo. If k is bigger than n, Charles and Toledo's one is faster. In our study, we give a tighter bound of the number of the changes, which is k cubed to the alpha k n square. So the learning time of the algorithms of Chu and Kadam is reduced to k cubed to the alpha k and square log n time. As the following table, our result dominates both algorithms in the time complexity. Thank you for listening to my presentation, and you can find more details in the recorded presentation or full version of the paper in archive.
Thanks a lot. Anyone have any questions from the audience?
I guess what's known about approximation? I don't know if it's already mentioned.
Approximate. There are some algorithms for the axis aligned polygon that not using rotation, then approximate this using divide angles to consider rotation. I do not remember exact result of this research, but this research exists.
Okay, there are some results, I see. Okay.
Now the running times close to linear in that case? Do you know? Is it like?
Can you ask your question again?
Yeah. So in the approximate setting, right? Are the running times close to order of n log n, or are they again expensive?
Expensive it is in the simple polygon and it's not polygonal region, and in this case, this simple polygon, and it is bound to log n when rotation is not considered.
Okay, so I had one more question. So you make extensive use of this edge-Warnay diagram, right? For the whole thing to work. I mean, are there other class of problems in computational geometry which have made a lot of use of this edge-Warnay diagram or the Delaunay triangulation? Some other class of problems?
This problem in AVD and EDT can be used in motion planning of convex polygonal robot in the polygonal domain. So I also reduced the time complexity to find the motion planning in convex polygonal robot in polygonal domain.
Okay. Thanks. Okay, thanks a lot. And let's move on to the next talk now.
Yes, hello. Can you hear me?
Okay, so the next talk is a faster algorithm for finding closest pairs in Hamming metric. And
Yes.
Floyd will be giving the talk.
Can you
8
hear me?
minutes for your talk and 4 minutes for Q&A.
Can you still hear me?
Yes,
Yeah, we
yes.
can. Yeah, we can.
Okay, sorry. Yeah, new setup. I wasn't sure. Okay, thank you. And welcome to my talk, a faster algorithm for finding closest pairs in Hamming metric. So my name is Floyd Zweidinger, and this is a joint work together with André Esser and Robert Kübler. As the title already suggests, we have together today a look into the closest pairs problem, which is in its bichromatic version defined as given two lists, L1 and L2, both of size n, and each element within these lists is a binary vector of dimension d. And the goal is now to find a distinguished pair x and y within these lists with relative Hamming distance gamma. So this is actually a very well-known fundamental problem of computer science with numerous applications in, for example, cryptography or coding theory as decoding random binary linear codes, or in the field of bioinformatics as genome analysis, and last but not least in the field of machine learning as similarity search of images. So it's a good thing to know the best algorithms, and therefore I start with the most easiest one, the naive search. This algorithm simply enumerates all pairs in our two lists. So for every element on the left side, we go through each element on the right side and check if these elements are our distinguished pair. Clearly, such an algorithm has a runtime quadratic in the size of the input lists. It's a quite simple algorithm, true, but nevertheless important because I'm going to use this one now throughout the talk as a building block. And the first framework we have a look into is locality sensitive hashing, or short LSH. So LSH tries to hash similar elements with a high probability into the same bucket. And afterwards, we are trying to apply a naive search on these buckets to faster find our distinguished pair. So what does this mean? So hashing down every element of our input lists means we are assigning a hash value to each element, which uniquely defines the bucket where the element is put into. And note, because of this locality sensitive approach, this is a probabilistic approach, meaning it can happen that our two elements, x and y, are put into different buckets. In this case, we are unable to find the elements via the naive search, and we have to reapply the whole procedure with a newly randomly selected hash function h2. And hopefully the two elements now survive in the same bucket as in this case. A quite similar approach to LSH is the so-called locality sensitive filtering, or short LSF. In this case, we exchange our hash functions with filtering functions, meaning we apply a filtering function on each element in our two lists, which is done for n different filtering functions. And again, because of the locality sensitive approach, this is a probabilistic algorithm, meaning it can happen that, in this example, only x survives, meaning it's not filtered out by every filtering function. It can also happen then that X and Y do survive in different filtered lists. And in this case, we are again unable to find X and Y because our naive search is not able to find them. So we hope for the best that X and Y survive in the same filtered list as in this case. This approach is then recursively reapplied for every filtered list and till the algorithm reaches the maximum depth. Let's say in this simple example, the maximum depth is 2. So we already reached the end, and our two elements X and Y survived in the same filtered lists. We are now able to find these elements via the naive search by searching through every filtered list in the end. So it's a well-known result that every algorithm based on this LSF framework has a time lower bound of n to the power of 1 divided by 1 minus gamma. So you already get the sense that this whole procedure is heavily depending on the choice of our filtering functions. In our example, well, in our paper, we choose the filtering function to be the distance on certain coordinates to a relative distance, to a randomly chosen element. Secondly, these filtering functions also greatly influence the two probabilities P and Q, where P is the probability that any element V survives, meaning it's not filtered out by every filtering function, and Q is the probability that our two elements X and Y do survive in the same filtered list. And it's actually one of our contributions in our paper that we are able to fully analyze this LSF framework purely on these two probabilities P and Q. Before we are coming to our contributions, let us have a quick comparison to the previously best algorithm by Otzorov, which is also an LSF-based algorithm for the closest pair problem. So on the picture on the left, you see our algorithm depicted in a solid line and the algorithm by Otzorov depicted in this dashed line. And you clearly see that for the most part, these two algorithms behave exactly the same, meaning they are reaching the time lower bound of LSF-based algorithms. Up to a certain point where suddenly our algorithm runs off to the bound of n squared. And this is actually, this makes actually a lot of sense because in this case, we are suddenly having the problem that if you choose two random elements of our two input lists, they are going to have an expectation, a distance of 1/2. But this is exactly the distance of our distinguished pair. This means that every element in our two lists has exactly the same distance as our distinguished one, meaning we have to enumerate every element in our every pair in our two lists, resulting in the naive search. On the other side, we have the algorithm by Otzorov, which somehow runs off until a certain point depicted by this dotted line where it's still applicable. So in general, you can separate this graph into two parts. The left one, which we call the low density part, which in this case, our distinguished pair is uniquely determined by the relative distance gamma. And from the point where the two graphs separate each other to the right, we are in the so-called high density part, which means we have to enumerate every pair in our two lists with the same distance gamma that our distinguished one. So stating this, our contribution is we are able to state or describe an algorithm which achieves the time lower bound in the high and low density case of the closest pair problem. We are able to significantly simplify the analysis purely based on these two probabilities P and Q. Additionally, we allow in our analysis for different input distributions other than the uniform one. And last but not least, we are actually able to to implement our algorithm and practically verify our algorithm. So I want to end my talk with a theorem stated in our paper that our algorithm is able to find the distinguished pair of the closest pair problem in time either the time lower bound of LSF-based algorithms in the low density case, or the number of closest pairs which in expectation do exist in the high density case. Thank you very much.
Thanks a lot, Lloyd. Do you have any questions? So I had one. So this theorem statement that you have, right? So I'm very curious. In the high density case, do you think, is there a way to improve the running time, like by even a log factor or something?
I don't think so. I mean, in this talk, I simply said we have to enumerate every element. I mean, this is not true because you only have to enumerate a non-negligible fraction of these elements to achieve a good probability to find X and Y. But in the end, this is simply a trade-off of runtime and success probability. When to have a constant success probability, you need to enumerate a high fraction of these elements.
But do you believe that's the right bound, or do you think there can be some can improve upon this?
To be honest, I don't know it. So it can be that the high density case can be improved, but only by constant, by a constant, not by higher.
So is this the hard case where everyone is away by distance of d over 2? Like, let's say all of them are randomly generated.
Sorry, can you state the question again?
Yes, I'm trying to understand which is the hard instance here. Like, let's say all the input strings are randomly generated, binary codes.
Mm-hmm.
So then the distance between any two of them and expectation is roughly d over 2. And there could be many of them. Is that the hard instance, or is that the easy instance?
I mean, if you define hard as
number of closest
has
pairs.
a higher runtime, then obviously the high density case is the more difficult one.
No, within that, I'm trying to understand which is the hard instance within the high density case.
You mean if the elements are randomly, uniformly selected, or distributed to a certain distribution?
Yeah, then second one.
Good question. I think the uniform is the hard case.
Hard case, okay.
But to be honest, I have to look this up.
Okay, nice. Okay, anyone else has any questions? Okay, thanks, Floyd. Let's then move on to the last talk, which I guess is being given by Rishikesh.
Yeah, can you see my screen?
Yes, I can see your screen and can hear you as well.
Okay.
So the final talk is by Rishikesh. He'll be talking about generalizations of length-limited Huffman coding for hierarchical memory settings. So,
Hi everyone. So I'll be presenting our work on generalizations of length-limited Huffman coding for hierarchical memory settings. This is joint work with Shashwat Banchor, Yogi Sabarwal, and Sandeep Sen. So first I'll explain you about Huffman coding, just a recap. So in Huffman coding, one can find prefix codes which are optimal in terms of code length using a simple linear time algorithm. So let's say if you have these characters and with these frequencies, in Huffman coding, first you pick the least 2 frequent characters, merge them, and you get a new set of characters. You keep repeating these merges with least 2 frequent, and you get a tree of this form. And for this tree, let's say to the left, you assign 0, and to the right, you assign 1. And let's say if you want the code word for C, it's 110. Based on that, we can generate the code words for all the characters. And the code length is nothing but the code word length times the frequency summed over all characters. Now, let's say if your input string is ACEA, so on, then the encoding string is nothing but replacing each of these characters with the corresponding code word. Now, decoding is nothing but once you have this bit string, you want to recover ACEA. And how do we do that? We just take the string and traverse this tree using this string. Let's say initially it's 0. So you see that it's A. Then you see it's 1, 1, 0. So you traverse 1, 1, 0. You see that it's C and so on. So this way we can decode once you have the bit string. So this tree traversal decoding would take number of bits much operations. Now there is a popular variant of Huffman coding, which is length limited Huffman coding. In this, so earlier our code word length was going as high as 5. So in that example, let's say if I restrict my code word length to be 3, and then I want to find the prefix tree, that is code word length is nothing but the tree depth for the prefix tree, which has code length optimal. For this, there is an order ND algorithm where n is the number of characters and d is the length limit or the tree depth which we are limiting. And again, once you construct the tree, which happens to be this tree for these set of frequencies, you can encode ACEA with 001 and according to the code words you have. Now again, to decode, we could have done a tree traversal, but here we know that the maximum tree depth is 3. So instead of doing a tree traversal, I can just maintain a lookup table of size 2 power 3. And in each lookup, I can decode at least one character. So in that way, I'll be able to, earlier in Huffman coding, if you're doing a tree traversal, we were taking number of bits much time. Here, since in each lookup, we'll decode at least one character, we'll take number of characters in this string much time. Now, we could have said that this can be done in Huffman coding too. But in Huffman coding, since there are n characters, the tree depth can be at most n. And if you're maintaining a lookup table, it should be of size 2 power n. That is huge, and we can't do that. So the realistic thing to do is maintaining multiple lookup tables and trying to decode any given prefix tree faster. Let's formalize it first. So let's say I have these characters and these code words. Now I'll define what a blocking scheme is, in which we use 2 lookup tables. And in this 2 lookup tables, we see how we decode this set of characters and code words. So for all the characters which have code word length at most 3, I'll just do one lookup for them. So let's pick B, whether it's 101 or 100, I can directly look up B using this lookup table. But whenever there is a 111, I am not sure whether E follows or D follows or F follows up. It depends on what's after these characters. For that, I maintain a second lookup table. So this can be this can be my cache memory and this can be my main memory. So this first lookup table, I'll assume it to be have access cost 1. And the second thing, let's say it has some queue. Now, with the procedure I said earlier, like once you have the string, you can initially look up 011. Then you see that it's A and you used only one bit. Then you move your pointer and then see 110 is nothing but C, and that way you decode the entire string. So if you decode this way, the access cost of all the characters which are in lookup table 1, that is ABC, which have code length less than 3, have access cost 1, and everything here will have access cost 1 plus Q. Now within this, so here the blocking scheme 3, 1, 2, Q is nothing but 3 is 2 power 3, the size of the first lookup table, and 1 is the access cost. 2 is the size of second lookup table, 2 power 2, and Q is the access cost of the second lookup table. So now given the blocking scheme 3, 1 and 2, Q, let's see what's the decode time for Huffman tree and the length limited Huffman tree in this. So for the Huffman tree, we saw that 34, 17, 11 have code word length within 3. So they'll have 1 access cost, and 3, 1, 1 will have access cost 1 plus Q. So the decode time will be 67 plus 5Q. For length limited Huffman coding, everything is within depth 3. So we can decode everything in unit time. So the decode time is 67. Now you can see that we are able to achieve a better decode time in length limited Huffman tree, but we are sacrificing on code length. So the natural thing to ask is, like, let's say I give a delta, which is a bound on decode time. Then I want to find the best code length possible for all the prefix trees which have decode time within delta. I'll formalize it. So you are given a blocking scheme which represents your memory hierarchy. And we are given a parameter delta, which is the permitted cost or the bound on the decode time we are setting. Now our goal of the problem is to determine the prefix tree, which minimizes the average code length or the code length. Both are the same. subject to decode time being at most delta. So if this delta is infinity, we are finding the prefix tree with best code length, then it will be the Huffman tree. If delta is 67 here in this case, it's nothing but the length limited Huffman tree because nothing can have less than one access cost. So for this problem, we give a p-task and we return a prefix tree which has code length at most 1 plus epsilon times the optimal code length. And this prefix tree will satisfy the decode time constraint we had. And the runtime of this algorithm is order n square by epsilon and some logarithmic terms. So the intuition behind our algorithm is the following. First, we get an exact algorithm for a more generic problem. For that, we use the dynamic programming approach for length limited Huffman coding due to Zolin and Gang. The runtime of that algorithm is n cube delta, where n is the number of characters and delta is the decode time limit we talked about. Since delta is an input parameter, this is pseudo polynomial in time. We use rounding technique to get a p-task, which is n power 4 by epsilon in time. Then we use some structural properties of the optimal solution to shave off another order n square factor, and we get an order n square by epsilon p-task. We also give polynomial time exact algorithms for some interesting natural extensions of LLHC. So we had a p-task for the problem, but proving our NP hardness or proving that it's polynomial remains open. And other interesting line of work is studying the empirical performance of our algorithms with real-world data sets on practical systems with hierarchical memory. Thanks.
Thanks, Rishikesh. Thanks, speaker. Anyone have any questions now?
So how hard did you try to prove NP hardness? Oh, and that's kind of an unfair question, maybe. But
we tried it for maybe 2-3 months, and we tried a lot of things, but it never worked.
Okay. No, I'm just asking because
So the problem is there are several other problems which are similar to length limited Huffman coding and stuff. There are like 3 to 4 other problems, and all of them have a p-task, and none of them have an NP hardness proof. There was one problem which is generalization of Huffman coding, not length limited Huffman coding, due to Fujiwara. In that they had an NP hardness proof, but they had a unsaid assumption too, which was a bug, and we also have talked about it in the paper. But other than that, like we couldn't find, there are no proofs in this. I think it's a very good area, like if you want to prove something is NPR.
So you're saying that even the previous, that Fujiwara's paper had a bug?
Yes, we fixed that, and like for the case they thought is NP hard, we gave a polynomial time thing in the paper. It's in the appendix.
I read your paper, I don't remember.
Okay. It's in the appendix.
Yeah, it's been a while. Okay. Sounds good. Thank you.
I had one question. So I was looking at the YouTube link, the full length talk you had. So there you had kind of formulated some optimization problem, and you had one constraint, right, in the end, which said summation of 2 to the power minus penalties has to be 1. Only then the prefix condition will be satisfied.
Yes. So
very easy to see, or is it I couldn't see it immediately.
It's not easy to see. It's something called Kraft's inequality. So
Kraft's inequality. Okay.
So let's say we said that in all these trees, these are prefix trees. That is, let's say if D was a leaf, if D was not a leaf and an internal node somewhere, then while I'm decoding F, I would, after like traversing till to, let's say D is near the 0.5, I wouldn't know whether it's D or something is happening afterwards. So there should be a prefix property which is being satisfied, right? And if that prefix property is satisfied, it must satisfy the Kraft's inequality another way. One intuitive way to see this is just try to make, let's say this is a tree of size 5, right? Depth 5. So expand A to have 16 more internal nodes, 2 power 4. B to have 2 power 8 more internal nodes. C to have, 2 power 3. C to have 4 more and D to have 2 more. Now sum of all these should be 2 power 5, right?
Okay.
Now just divide this entire thing by 2 power 5. So each of these will correspond to 2 power minus 5, 2 power minus 5, 2 power minus 4, 2 power minus 3, and so on. Whenever a tree is prefix tree, this sum is less than 1. Yeah, so that part I see. In one direction it goes, but does it have to be in the other direction as well? That looks. Yeah, the other direction is construct. You can do it in a constructive way. So pick the least thing and first Okay, so you can pick the maximum of all the depths, multiply the entire both sides by that 2 power that maximum. Now each thing will represent some internal nodes protruded to the maximum level, right? Based on that, you can construct similar to this.
Okay.
It's not trivial, but it's like standard class inequality.
Okay. Okay. So one final question I had was, you said in regular Huffman coding, how much time does it take to decode? So how do you find time there? Like,
yeah. So one is, if you look at in our model, like we could do it in this way, where we have a blocking scheme and we formally define decode time. There we can say this model is independent of what the tree is. For Huffman coding, we have a decode time and everything. But generally, just to explain the intuition of decoding, I explained a simple tree traversal. So here, if we have the input bit string here, and we are just not using lookup tables or anything, doing a simple tree traversal to find the codes ACEA. Then in the first step, we look at 0. So we discover that it's A. When we do 1, 1, 0,
yeah.
we see that so you are doing number of bits many operations.
Yeah, but let's say you had a lookup table, right? Like you have on the right. And let's say all of it is stored in the
table here.
No, just a second. So let's say all of it is stored in the main memory. So you can do the lookups in constant time, right? Per character. Or that's not possible.
You can do a lookup table if you have a lookup table of size 2 power depth.
Why do you need 2 to the power is what I'm trying to understand. We can't use simple hash tables which won't require 2 to the power depth number of entries. Can a simple hash table work here?
Just a minute. There are lots of. So how will you assign these characters to the hash table? In the hash table, the entries are of 2 power d, right? No.
No, so you compute the code for everything and you just store all of the codes in the hash table. And whenever this encoding comes to you, you try to.
So how many bits do I look up at one time?
So I'll start with 1 bit, then start with, if that is not there, then do 2 bits, 3 bits.
Yeah, if we do that, then you are taking in the worst case order n time again, right? For each lookup, that becomes expensive.
But then I know that the probabilistically, I mean, that will not happen very frequently. The deepest one, which is.
So you are saying first you do one lookup of 1 bit, then you'll do lookup of 2 bits and so on, right? So that will be equivalent to just doing a tree traversal, right? Like let's say if it's k bits, when you're doing a k lookup, you already did it k times, right? So that will be just the number of bits many operations.
Seriation. Okay, good. Okay. Does anyone else have any questions for Rishikesh? Okay, so let's thank all the speakers in this session. And yes, we can close the session now. Thanks, everyone.
Thank you.
Okay. Okay, shall I start? Okay.
Please start.
Hi everyone. My name is Chetan Gupta, and I'm going to present our result, reachability and matching in single crossing minor free graphs. This is a joint work with Samir Datta, Rahul Jain, Anish Mukherjee, Vimal Raj Sharma, and Raghunath Tiwari. Yeah, so let me first define the reachability problem. So in the reachability problem, we are given a graph G and two vertices S and T. We need to answer whether there exists a path from S to T or not. So this problem is a complete problem for the class NL, which is the class of problems that can be solved by a non-deterministic Turing machine in log space. UL is a special subclass of NL, which is a class of problem that can be solved by a non-deterministic Turing machine in log space, such that the Turing machine has at most one accepting path on each input. So traditionally, a non-deterministic Turing machine can have many accepting paths on one input, but a UL machine has at most one accepting path on each input. So by definition, we know that UL is a subset of NL, but we do not know whether NL is also a subset of UL or not. Since this reachability problem is a complete problem for the class NL, if we can show that reachability can be solved in UL, this will imply that these two classes are equal. So Reinhardt and Anders show that if we can efficiently construct a polynomial size weight function for graphs, such that there exists a unique minimum weight part between every pair of vertices in the graph, then the reachability problem can be solved in UL, and this will imply that N is equal to UL. Perfect matching in a graph is defined as the set of disjoint edges in a graph, such that each vertex fall on exactly one edge in the set. And in the perfect matching problem, we are given a graph, and we need to answer whether there exists a perfect matching or not. So polynomial time sequential algorithm is known for perfect matching, but there is no fast parallel algorithm known for perfect matching. So MC is a class of problem that can be solved by fast parallel algorithms. So Allender, Reinhardt, and Zhao showed that if we can construct weight functions for graphs such that there exists a unique minimum weight perfect matching with respect to that weight function, then perfect matching problem can be solved even in SPL, which is a smaller subclass than NC. So previously, such weight functions have been constructed for various special classes of graphs, like planar graphs, bounded genus graphs, K33 and K53 graphs, and log n genus graphs. But for general graphs, we still do not have any polynomial size isolating weight function that can be constructed efficiently. So in this result, we construct polynomial size path isolating and bipartite perfect matching isolating weight function for single crossing minor free graphs in log space. And as a corollary, we show that bipartite perfect matching in single crossing graphs can be solved in SPL, and reachability problem in single crossing minor free graphs can be solved in UL. So now we'll see the construction. So let me first define what is a weight function. So a weight function is a function that assigns an integer to every edge in a graph, and we call a weight function schizometric if for all edges in the graph, weight of an edge E is equal to negative of the weight of E reversed. This ER represents the edge E with its direction reversed. Now, if we know that, we can argue that if we have a schizometric weight function that gives non-zero weight to all the cycles in a graph G, then it will isolate a path between every pair of vertices in G, and it will also isolate a bipartite perfect matching in G. So I'll just show how such a weight function isolates the path between every pair of vertices in G. And the similar argument can be used for arguing about isolating a bipartite perfect matching. So assume that we have weight function W, which is a schizometric weight function, and it assigns non-zero weight to all the cycles in the graph. And now, for the sake of contradiction, assume that we have two paths P and P prime between a pair of vertices U and V, such that both P and P prime are of minimum weight. So since they are of minimum weight, they must be of equal weight. Now, if we look at another graph where we reverse the direction of edges along one of the paths, now these two paths form a cycle. And by our assumption, we know that every cycle in this graph has non-zero weight with respect to our weight function. So from this, we can conclude that weights of P and P prime cannot be equal. So now we will construct such a weight function for single crossing minor free graphs. Let me first define what is a single crossing minor free graph. So first, what is a single crossing graph? So a single crossing graph is a graph that can be embedded on a plane such that its edges intersect on exactly one point. So here, this is that point. So this is a single crossing graph. And for a given single crossing graph edge, we call all H minor free graphs as single crossing minor free graphs. So it is known that single crossing minor free graphs can be decomposed into planar graphs and constant tree width graphs. So assume that this graph G on left is a single crossing minor tree graph. It can be decomposed into smaller subgraphs such that each of these subgraphs is either planar or of constant tree width. So what we get from this decomposition is that if we have a cycle in single crossing minor tree graph, then that cycle will either be contained completely inside a component on the right, or it will span over more than one components on the right. So here, if we look at this cycle, yes. Was there a question? Oh, okay.
Just 1 minute left. That's all.
Oh, okay. So yeah, so if we look at this big cycle, we can see that it has been decomposed into smaller cycles. Now our aim is, and if we have a skew-symmetric weight function, then we can say that it also preserves non-zero. It also preserves the weights. So sum of weights, we can show that sum of weights of these smaller cycle will be exactly equal to weight of this big cycle. Now, what we do is that we look at the, so we call this tree the component tree of the graph. Now we replace each constant tree width component in the graph by its own tree, its own component tree, wherein that component tree, these components are, all of them are of constant size. So finally, we get a component tree in which each component is either planar or of constant size. Now we construct our weight function, which assigns non-zero weight to all the cycles in the graph. So we know that there are two kinds of cycles, one which are completely contained within a component, and one which spans over more than one component. So W1 assigns non-zero weight to all the cycles which are completely contained within a component. W2 assigns non-zero weight to all the cycles which span over more than one component. Yeah. So for planar component, we can use the weight function which has already which is known already known. So we can use that weight function for planar component, and it will give non-zero weights to all the cycles which are completely contained within a planar component. And for constant size component, we can use exponential weight, and that will give non-zero weight to all the cycles which are completely contained within a constant size component. And W2, which assigns non-zero weight to all the cycles which span over more than one component, works in the following way. So assume that we have this component tree and it's a rooted tree. So W2 is start to assign weights to the cycle from in bottom up. Yeah. So these cycles in the leaf node get some constant weight, and as we increase the level, the weights of the cycle increase by a constant factor. So if we can ensure that this component tree has depth log n, we get a polynomial size weight function for the whole. Yeah. Okay. Yeah, I'm done.
I'm so sorry to just interrupt, but we kind of have a tight timeline here.
Yeah, sure. Okay. Yeah, no problem.
So I think we are well past the question time. So if there are any questions, please post to him on the chat or after the session that we can take it up. Is that okay? Please, let's thank the speaker and clap for him.
Yeah, thanks.
So please, may I call upon the next speaker? Suryajit, so let me just give a brief introduction. The next talk would be on functional lower bounds for restricted arithmetic circuits of depth 4, and it will be given by Suryajit Chilara. On to you, Suryajit.
Hi, so I'm going to talk about some work which falls in the intersection of Boolean circuit complexity and arithmetic circuit complexity. So can you, one second. Yeah. So, so there's a Boolean function hierarchy that we know, and so in this hierarchy, one of the famous questions that is studied is like, is P a complete? I mean, is a strict subset of NP or not? So this is a very famous question which has been unsolved for like decades now. And in this Boolean function hierarchy, there are like other questions which are unsolved as well. For example, there is this class of functions which actually which are called counting problems. So this is sharp P, and we don't know if sharp P is a strictly larger set than say a set ACC0, which is a set of functions that are computable by constant depth circuits over and or not and mod. Okay, so not just P versus NP, there are many questions that you can ask in this Boolean function hierarchy. So sharp P versus ACC0 could be thought of as a coarser question than P versus NP in this hierarchy. So let's look at the smaller class that we have actually talked about. So this class ACC0 is a set of functions computable by constant depth circuits with and or not and mod m gates. Right? For mod m where m is an integer. And we would like to prove, so if you want to separate a particular class from a larger class, you want to show that there exists a function which is not in the class ACC0, and it lies strictly outside the class ACC0. And towards that, like the first lower bound that was proved against ACC0 in the uniform setting was by Eric Allender and Vivek Gore, who showed that permanent, which is a function in sharp P, it is not in uniform ACC0. And later Williams showed that there is a function which is in an EXP, non-deterministic exponential time, such that it cannot be computed by small non-uniform ACC0 circuits. So this was later improved to NQP. So now you may ask, so in a uniform setting, a function which is in sharp P, such that it cannot be computed by ACC0 circuits of small size. Similarly, like non-uniform setting, can you actually find a function which is in sharp P? So this is an open question. And so one of the interesting things to approach lower bounds of this form, so all the lower bounds shown in the previous slide of Allender and Gore, Williams, Murray-Williams uses characterization for small depth circuits, which is every function which is in AC0 can also be computed by a deterministic depth 2 circuit. So depth 2 circuit is of the following form. You have some symmetric function at the top, and into the symmetric function, quasi-polylog many ANDs feed into, and each of these ANDs depends on polylog many variables. So this is a depth 2 circuit which recognizes a function in AC0. So now, what is observed by Forbes, Kumar, and Saptarishi was the following. So you take a symmetric function. If you assume your field to be large, you can actually convert it into invariant polynomial, where the symmetric polynomial can be expressed as a invariant polynomial in a variable, single variable. That single variable is given by summation of inputs, summation of its inputs. And using this fact, you can convert your expression, which was the depth 2 circuit, you can algebraize into the following form. So what they actually observed is any function f in AC0 can also be computed algebraically as sums of powers of polynomials, where the sums, the number of summits is at most quasi-polynomial, and each of these polynomials, the QIs, depends on, so it is such that every monomial in QS is supported at most polylog variables. So we will call these expressions as sigma power sigma pi. So basically, what it says is every function which is in AC0 can also be computed algebraically using the sigma power sigma pi expressions. The sigma is a sum. This wedge that you can see is a power, and sigma pi is a summation of monomials. So this is a representation that we'll henceforth use for expressions of the form sums of powers of polynomials. So now one strategy towards proving ACC0 lower bounds is as follows. So we want to show that there is a function f such that fix a domain. So let's say we'll fix a domain to be 0, 1 because we are working with Boolean functions. Now over this domain, you can build an evaluation table. So one of the ways to show ACC0 lower bounds is to say that there exists a function such that the evaluation table of this function is not equal to the evaluation table of any small sigma power sigma pi expressions. So if you can show that, and you can also show that f is computable in a class that is not much larger than ACC0. So we have separations from NQP and ACC0. So preferably we want f to be in a class which is much smaller than NQP. So rather smaller than NQP. So preferably sharp p at this point of time. So towards that, what we show is there is a function f which is computable in GAPL, which is a much smaller class than sharp p. However, we show that the evaluation table of this function f is not equal to the evaluation table of small but bounded individual degree sigma power sigma pi expressions. What do I mean by this? So you have sigma power sigma pi expression compute polynomials. Now we take all those polynomials computed by sigma power sigma pi, which are of bounded individual degree. So what is a bounded individual degree of a polynomial? Bounded individual degree polynomial. So degree of f with respect to each of its variables is bounded by some quantity r. So now what we say here is look at the evaluation tables of all polynomials which are of bounded individual degree and are computed by small sigma power sigma pi expressions. And those evaluation tables, all these evaluation tables are not equal to the evaluation table of f. So there is an explicit function f. And I repeated the argument here. And the way we obtain this result is by proving functional size lower bounds for restricted arithmetic circuits. So let me just tell you what this restricted arithmetic circuits are. So arithmetic circuits are directed as cyclic graphs which compute polynomials. I'm just going to. So here, so you have arithmetic circuits which are directed as cyclic graphs. You can think of them as product, sum, and this powering is a restriction of a product where all its inputs are the same. So sigma power sigma pi expression is a depth 4 circuit such that the product gate at the top has inputs which are same. So now let me just tell you what the functional lower bounds are. So how am I doing the time? 1 minute, right?
1 more minute, yes.
Okay. So what do I mean by functional lower bound in this algebraic setting? So I want to show that the evaluation table of any circuit. So let's take a type of circuit C. Here it is sigma power sigma pi. And let me put up the threshold S. I want to show that for sigma power sigma pi circuits with a threshold S on size. So if I look at their evaluation tables, that evaluation table is not equal to that of P. So that is the thing. So let me just say, well, how do you do this? So the way we do this is by showing that there exists an explicit polynomial P such that it is not functionally equivalent to polynomials of bounded individual degree that are computed by small sigma power sigma pi circuits. So this is step 1. And there is step 2, which says that there is a function f that simulates the evaluation of this polynomial over 0, 1 power n over the domain. So this is, so if I have a minute, I can just tell you what the polynomial of interest is. So there is this, the polynomial of interest is iterated matrix multiplication. So iterated matrix multiplication can be thought of as 1, 1 entry in the product of generic matrices, each of whose entry is a distinct variable. And this polynomial is known to be efficiently computable it has polynomial circuits, and in particular, it has a depth 4 circuit of size n to the root d. So this polynomial is parameterized with respect to n and d. So basically, the proof of step 1 goes via defining a complexity measure such that this measure differentiates like bounded individual degree polynomials that are computed by small sigma pi circuits and the polynomial of interest. So there is this monstrous expression that I've put out here. So this is the measure that is defined for this. So this measure differentiates between both of these kinds of polynomials. And this is the main theorem. So we say that like any polynomial, so n and d are related as follows. So we say that any polynomial of bounded individual degree r that is computed by a sigma pi expression of size at most n power k. If it is if p is a polynomial of bounded individual degree r and is computed by sigma pi expression of sizes, then s must be n power omega k if p is functionally equivalent to the iterated matrix multiplication polynomial. So I'm just rushing through a lot of things. So there is a formal theorem. So here the parameters n and d show up here. And we know that evaluation of iterated matrix multiplication is in GAPL. So this can be found in a result in a paper of Vinay. It was in Structures 1991. Yeah. So what I would say is improving this result could lead us to a separation of ACC0 from GAPL. Okay, I'll stop.
Okay, so let's thank the speaker first. And we have about 2 minutes for some questions.
So yeah, thank you.
I guess there aren't any questions. If somebody thinks of something, they can please feel free to ask him on the chat or maybe after the sessions when we have a break. Is the next speaker ready?
Yes.
Nice, Rick. So can you please share your screen? Okay, don't just start it. Hold on a minute. Okay. So let me just say that the next talk is on towards stronger counterexamples to the log approximate rank conjecture. The authors are Orkadev Chattopadhyay, Ankit Garg, and Suhail Sharif. Suhail will give us the next talk. On to you.
Thank you, Sushmita. Right, so this talk is about counterexamples to the log approximate rank conjecture. And it was written with Orkadev and Ankit, but it's not really the log approximate rank conjecture that will be the main highlight of this talk. This talk is going to be about a quite fundamental question. You're given functions g1 to gt, and you want to analyze the complexity of the function f, which is defined as it should take the value 1 if any of the functions gi takes the value 1 on their respective inputs. Now, this is a well-studied problem. It crops up everywhere, but what we're studying in this paper is a quite related and still interesting question of you just have one input x and you want to know, does any of the GIs output 1 on that single input x? And this is related to the approximate rank conjecture, and the relation is quite simple. So if you take your GIs such that each of them have disjoint sets of 1 inputs, then when you construct the function f as the OR of all these GIs, you can also think of it as the sum of the GIs, in the sense that if you take the indicator vectors of each of the GIs and you add them up, you get exactly the indicator vector for f. So an algebraic measure such as rank would be subadditive. So the approximate rank of f would be approximately the approximate rank of g times t, because we're adding t of them. And what the log approximate rank conjecture would say would then be that the cost of computing f would be polynomial in the logarithm of t and the cost of computing g. But now one might ask, can't you choose your GIs such that you're forced to actually compute each of the GIs. If you can do this, you would have omega t cost instead of polylog t. And this isn't always possible. For instance, in deterministic communication complexity, you can actually get polylog t in cost of computing G. But in the case of randomized communication complexity, it actually is possible to choose GIs, which actually give you omega t cost. And that's how we actually disproved the log approximate rank conjecture in a previous paper. And that counterexample was with Arkadev and Nikhil. And it used very simple GIs. So all the GIs looked like subcubes here. So G1 would output 1 if and only if the coordinates 1, 2, and 3 of x are 0, 0, and 0. G2 would output 1 if 1, 4, and 5 are 1, 0, and 0, and so on. And these are chosen so that each of the GIs have disjoint 1 inputs. But another important property about this set of GIs is that each coordinate, for instance, x1, appears in only 2 of the constraints, G1 and G2. x5 appears in only G2 and G4, and so on. Now, this property is useful for the lower bound because Scherer's lemma, it's a very elegant lemma. It lets us compare the entropy of any distribution A with the entropies of the marginals of the distribution on specific subsets of coordinates. So the marginal of a distribution is understandably important in our case because, say, the marginal of A on the coordinates 6, 4, and 3 is exactly what's going to give us some idea of whether G3 is true or false. But it's not clear yet how Scherer's lemma helps us. And if you rewrite it, it's still not very clear, but this is the interpretation that I'm going for here. So if a distribution A affects many of the TIs, so if a distribution is going to help you solve a particular GI, it must actually help you. You should be able to see it in the marginal of that distribution on TI. So in that sense, it's affecting many TIs. And mathematically, what that corresponds to is that this quantity is omega 1. And what Scherer's lemma would imply is that if for many of the TIs, this quantity is omega 1, then n minus h of A should actually be large. All of these omega 1s are going to add up. And so h of A is actually going to be much smaller than n. That means that A must be a small distribution. Okay, why am I talking about distributions? If you have a cheap cost protocol, then that would imply that there's a large distribution which helps in solving many of the GIs. So the fact that if a distribution helps in solving GIs, then it must be small, means that it's actually hard to simultaneously solve the GIs. So in particular, solving F is hard. That's what I mean by simultaneously solving the GIs. Okay. Now, what we do in this paper is we try to generalize our previous counterexample. We look at GIs that are not just saying a coordinate is equal to some value, but it's saying that a parity of a subset of your coordinates is equal to some value. So there are multiple such constraints, and each GI looks like the AND of such constraints. And another way to phrase this is that a GI accepts X if and only if X lies in a specific affine subspace of F2 to the N. And the question is again the same. Which such choices of GIs are going to let us prove that it's hard to simultaneously solve these GIs? And an answer for this comes from the notion of subspace designs. So this is one possible way in which GIs can be hard to simultaneously solve. And these have been studied before in the context of pseudo-randomness and coding theory, but we noted that it's actually quite useful for us. So subspace designs are these spread out set of subspaces, which have, very informally speaking, this property. So right now, let's just ignore these words over here. If a distribution A affects most of the TIs, by which I mean they help in solving GI, then A must be small. Now, this is exactly the statement that gave us our lower bound in the original counterexample. So the only catch here is the part that I scratched out. And that's saying that this holds only when, or this is at least guaranteed to hold, only when your distribution A is uniform over an affine subspace. So it doesn't give us our complete communication lower bound, but it does actually give us a lower bound in the model of parity decision trees. So this is hard for a randomized parity decision tree. So, okay, what are we doing in this paper? The previous counterexample to the log approximate rank conjecture showed that there is a function f where the randomized communication complexity, I'm not going into what these things are, but it's at least the fourth root of the approximate rank of f. And the best upper bound that we have in general is order approximate rank of f. So there is some gap here. And you can ask, where does the actual, where is the tightness? And we, in this work, we suggest functions that we hope will prove that the lower bound can be improved to at least the cube root of the approximate rank of f. And to back up this suggestion, we actually proved the result for randomized parity decision trees, that such a result is true in the setting of randomized parity decision trees. And we also provide conjectures that would extend the result from randomized parity decision trees to randomized communication complexity. Now, this field is, this is a very sought after result to say that a lower bound for randomized parity decision trees would lead to a lower bound for randomized communication. And so this would be an interesting, say, toy case to solve. Can we at least prove for this class of functions that it does actually extend? It seems like a very structured class of questions, so it should be interesting to see how this plays out. Now, what are these interesting conjectures that I refer to? So I'll mention the main one here. So it's very similar to what we wanted. We want to say that if a distribution A affects many of the TIs, so for many subspaces T from our subspace design, if the distribution A is helping in solving GI, then the distribution must be small. So there are some parameters that I've highlighted in orange that I'm not going into here. But this is the crux of the conjecture. And if this is true, then it would immediately give us our lower bound. And it's very tempting to ask whether this is true or not, because we know that this is true when say the distribution is uniform over an affine subspace. Otherwise, we know it's true when the subspace design has a nice structure, like in our previous counterexample. So there are many subcases in which this is true. Now we're asking, is this true in general? And this conjecture is still open even if you have random subspaces. Now, if you have random subspaces with certain parameters, that would imply that it's a subspace design. But even in the case of random subspaces, even though we have more tools that we can use there, it's still not clear whether this conjecture is true or not, although we believe it is true. I think that's my time.
Is that over, your talk?
Yeah, so I can stop here. I can talk about what this means, or I can continue.
Let's thank the speaker for one. You have about 2.5 minutes for some questions. Any questions from the audience?
So you mentioned that you have you formulate many interesting conjectures. This is one. So what is are the others very different?
I didn't say many, but
more than one, right?
Right, more than one. So one is the.
Yeah, so are they of different flavors, or are they?
No. They're the same type of conjecture. They're not of different flavors.
Okay. Yeah.
Like there aren't any more questions. I'll still keep the clock running. Maybe Meena, you can share your screen in the meantime just to set us up.
Okay.
Don't just start yet. I'll let you know. Okay, so just as a reminder, I'll restate that the policy is to have 8 minutes of talk and 4 minutes of question time. So in some cases, everybody, I mean, I can clearly feel constrained by the 8 minutes. So we can have a little longer talk, but then the question time will get reduced. Okay, so perhaps we can start now. The next talk is on simple decision tree rank. The authors are Yogesh Dahiya and Meena Mahajan. Meena will give the next talk. On to you, Meena.
Yeah, thanks everybody for coming here. I'm going to give a very short presentation about what this paper is about. The longer talk video has been recorded actually by Yogesh, not by me. So I hope that there isn't too much of a disconnect between what is being said here and what is said there. So what we are trying to understand is how complex is a Boolean function, and we are going to look at families of Boolean functions. The nth function typically is a function from n bits to 1 bit, like the constant function or parity function or whatever. We want to understand how complex the function is. And the ways to understand complexity, well, the obvious way which would be most interesting is to understand how hard is it computational. That's really what we are interested in. For this, we would need to specify the computational model, and we would need to specify what is the resource that we are measuring in that model. But there are also several what I like to think of as intrinsic measures for a function. They may be descriptive or structural measures, depends on your view, which these are measures of the function which are defined completely independent of the computational model. For example, there's sensitivity, there's certificate complexity, there's degree or approximate degree, Fourier sparsity. These are really measures of the function independent of how you are going to go around computing it. So these particular measures that I've listed here are all known to be polynomially related to each other. And what we do expect is that there is a relationship between the intrinsic measures, which kind of tell you something about the function, and the computational measures. So the specific computational model that we are interested in which we want to understand hardness, is the model of decision trees. And the decision trees, probably almost everybody here knows what they are. Here's a very quick run through. So here are 3 different types of decision trees. Adaptively, you query some property of the input. Like here, I'm querying the inputs a plus b together. Do they add up to at least 1? Yes or no? Then you, depending on the answer, you do something else. Or you could query whether the sum is odd, or you could just query a single variable at a time. So depending on what type of queries are allowed, you get linear threshold functions as queries. You have linear decision trees. Odd even queries, you have parity decision trees. Querying a single variable at a time, those are what are normally called just decision trees. But to emphasize this fact, in our title, we have put in the word simple. So these are all decision trees which are computing the same function. Okay? And they do look quite different because the nature of the query could change what it is that you can do quickly. So what would be the complexity measures with the decision trees? Well, the depth of the tree is an obvious measure, and it measures the query complexity. So if the input is unknown and you're querying some property about the input, in particular, you're querying a variable 1 by 1, how many queries do you need to make before you are sure that you know the value of the function? And this is the measure which is known to be polynomially related to all those intrinsic measures that I mentioned. The size of the decision tree is also another interesting measure. It measures, I mean, if you're going to store your Boolean function, you think of the decision tree as a data structure which is storing the function, and then the size is just the space needed to store it in this representation. So some obvious bounds between decision tree depth and decision tree size. So when I say depth of f, what I mean is the minimum depth of any decision tree which computes f, size of f, the minimum size of any decision tree which computes f, and of course the trees which witness these need not be the same. Okay. So what we are interested in here is a relatively less studied measure called the rank of a decision tree, and what we look at is how it compares with other measures for the function. So what exactly is this measure? Well, the rank of the function, as for the other measures, is the minimum rank of a decision tree for f. So what is the rank of a tree? It's, in some sense, is a measure of its branching complexity, how much the tree branches out in different parts. I'm not going to give a formal definition here, but this is a very useful way to think of it. Is the maximum depth of a complete binary tree that can be embedded in this tree. So unary nodes, you just shrink, take a subtree of the tree, shrink the unary nodes, and then how big a complete binary tree can you get? So in the literature on trees, this is a very well-studied thing. It's called a Houghton-Strahler number. And so now we are looking at various decision trees for f. Each one of them comes with its own rank, and then you take the minimum such rank. So this rank has been looked at in the literature before, though not much is known about it. There are some very obvious bounds. Rank, the depth is at least as much as the rank, because you can embed a tree of that depth in this. The rank is related to the logarithm of the size. Again, if you can embed a complete tree of depth r, then the size must be at least 2 to the r. So this is something that is known, and what we want to do is to look at this a little bit beyond that. What more can we say in terms of rank? Do we think that rank can give us more information about the function? So rank is interesting because decision tree rank for a function, because it does show up in many places. It's not that we've pulled it out of the hat somewhere. In learning theory, in fact, this is a paper by Ehrenfrucht and Häusler. This was the first paper which actually formally defined the rank of a Boolean function, and they showed there that if a function has a decision tree of constant rank, then that function, that decision tree in particular, can be efficiently learned in Boolean SPAC model. It shows up in circuit complexity. If you're looking at linear decision trees, then constant rank implies that there are small TC0 circuits of depth 2. It shows up in proof complexity, where it is useful for showing lower bounds. If the related search problem has large rank, then you can prove, then it implies that a certain kind of proof must be very large for those formulas. So for Boolean functions, rank can reveal information. When we are looking at the rank of a decision tree, it can reveal information which is not implied by the more standard measure, which is depth of a decision tree. And in particular, there is this very nice prover-delayer game, which completely characterizes the rank of a function. In fact, this comes about from the proof complexity literature, and it's kind of implicit when you string together constructions in these 3 papers. You set up a game between 2 players. The prover queries some unset variable, and the delayer can either say, I don't care, you choose whatever value, and then the delayer gets 1 point, or the delayer gives the value of that variable, and then the delayer does not get any points. And the game ends when enough variables have been queried and their values set so that on the restriction, the function is a constant. And the value of the game is the maximum k, such that no matter what variables the prover queries, no matter what choices are made by the prover when the prover has a choice, the delayer can always score at least k. And this is the theorem that game value is for a function f is exactly equal to rank. As I said, this is not really our theorem. It is there in this work. It is known in this literature, but it is not explicitly stated, and we kind of extract it and state it in a self-contained way. So then we move on to relating rank to certificate complexity. The certificate complexity of a function is the smallest k, such that for every input x, there is some subset of size k of the bits, where if I tell you the value of x on these k bits, then you know the value of the function. And well, for the depth, which like I said is a well-known measure, it's known that depth lies between the maximum, the certificate complexity, and the product of the 0 certificates and the 1 certificates. What can we say analogously for rank? Well, we tighten the upper bound a little bit. Instead of C0 and C1, we can say C0 minus 1, C1 minus 1. But the lower bound, in fact, we show that you cannot give a lower bound in terms of any of these measures. I see that I have reached my 8 minutes. I'm going to take another minute. So the other thing that we look at in our paper is composed functions. So when you compose 2 functions, you think of the composed function f of g, where you have multiple copies of g operating on disjoint inputs, and then their outputs are fed into f. For a depth of a decision tree, there is this really nice result which says that it is exactly multiplicated. Depth of f composed with g is exactly depth f into depth g. Can we say something analogous for rank? Well, you cannot give such a result purely in terms of rank, because the rank can of the composed function can grow arbitrarily even when f and g are of constant rank. But what we can show is something like this. So the rank of the composed function depends on the depth of the outer function and the rank of the inner function. And the upper bound is shown by giving by modifying the construction here. The lower bound also, I mean, it's kind of a very careful adaptation of the result which is known for it. So in the paper, the main the bulk of the paper is made up of these 3 things. For the prover-delayer game, we give a self-contained proof so that you don't have to dig through 3 different papers. We give detailed constructions for the upper bounds of composed functions and the 2 upper bounds that I mentioned. And we calculate the rank exactly for some functions, both by direct combinatorial arguments as well as by prover-delayer strategies. And this exact calculation helps us to show that all the bounds that we have obtained are indeed tight and cannot be tightened any further. So I invite you to go and take a look at either the longer video or the paper. Thank you for your attention.
Okay, thank you, Meena. Let's clap. Let's thank the speaker. So you have about 2.5 minutes for some questions.
Hey, hi, Meena. Just wanted to ask, probably I missed it, but are the depth and the rank, they cannot be polynomially related? Is that already known?
Yes. So for instance, for the simple function and on n bits, in the decision tree model, the depth is n. The adversary can force you to query all n bits, but the AND function has rank 1 because the decision tree for AND looks like a comb, And if you want to embed a complete binary tree in it, you cannot embed a tree with more than 2 leaves.
I see. I see.
Yeah. So rank is constant and depth is growing. So there cannot be a polynomial relation. Yeah. In fact, that's what we used to say, that even for composed functions, you cannot have a bound purely in terms of rank. You have to involve depth.
Because it can, like, the rank can stay constant and depth can grow indefinitely.
Yeah.
And sorry, if I may ask another question.
Please go ahead.
So just this lower bound for the composition, can you give me some idea? Like, is this the same as this adversary argument, or?
So we take a, yeah, okay. I mean, it's not adverse. We actually, we need to define a weighted version of the depth. So we pull out from the tree which witnesses this rank, a tree of this depth in some sense.
Okay. Thank you.
So Jackma, please go ahead.
So Meena, there was a connection to learning theory. So I was wondering, is there a connection between rank and VC dimension?
Not that I know of. Okay. Yeah. So the connection to learning theory was for learning functions in the pack model if they have constant rank decision trees. But I have not seen such a connection, and I do not know how to make this connection.
Thank you.
Are there any more questions? Okay, let's thank Meena again for a very nice talk. So the next speaker, could you please share your screen? Let's get sort of ready.
Hi, can everyone see the screen?
Yes, just give me a second. Okay. So the last talk of this session is Chang's lemma type bounds for Boolean functions, and it will be given by Tulasi Mohan Molli. Tulasi Mohan, on to you.
Hi everyone. This is joint work with Saurav, Nikhil, Rajat, Manasvi, and Swagato. So yeah. So for the Boolean function is a function from -1 to the n to -1. So every Boolean function can be uniquely represented as a linear combination of these parity functions, and the coefficients in front of these parity functions are the Fourier coefficients. For example, chi alpha is just a product of xi such that alpha equals 1. Yeah. For example, and is a Boolean function which takes the value -1 when on the all -1 input, and it takes the value 1 on every other input, and it has the following Fourier representation. You can check that when you plug in the all -1 value, 1 input, you get the value -1, and when on every other input, this expression outputs the value 1. And another function which shows up majorly in our work is the addressing function. So addressing function has 2 types of inputs. One address bits and the other the target bits. So there are lofty address bits and the target bits, and these lofty bits correspond to the locations in target locations, and the function outputs the contents of the in the address corresponding to input y. And you can this is the Fourier expansion of the addressing function looks something like this. And yeah, so here are some Fourier analytic measures which we are interested in. One is the first thing is the support. Support is all the alphas such that f alpha is non-zero in the Fourier expansion, and sparsity of a Boolean function is just the size of the support or the number of non-zero Fourier coefficients in the Fourier expansion. And another thing which you look at is the Fourier dimension. So Fourier dimension is look at the dimension of the F2 span of the vectors in the support, and you look at the dimension of that. That is what we call Fourier dimension. And another interesting quantity which we look at is this quantity called max entropy. Max entropy is look at the smallest Fourier coefficient in absolute value and take the inverse of that, That is a max entropy. And another quantity which we look at is this max rank entropy. So it is the smallest number t, such that if you look at the if you look at the alpha, such that f hat alpha is greater than 1 by t, they span, they generate all the elements in the support. So max rank entropy, yeah, I hope that's clear. We'll look at an example in a bit. So weight of a Boolean function is the number of -1, is a fraction of -1 in its truth table. Okay. So for example, and has this Fourier expansion, and you can check that its sparsity is 2 power n because all entries are non-zero. All the Fourier coefficients are non-zero. Its dimension is n, and max entropy is 1 by 2 is 2 power n minus 1, and so on. And yeah, the thing to note here is that the dimension and sparsity dimension is logarithmic in the sparsity for and again similarly you can compute the sparsity, dimension, max entropy and max rank entropy for the addressing function looking at its Fourier expansion. Here again the thing to note is that the sparsity is quadratic in the dimension. So previously for these are exponentially separated, and for addressing the relation is quadratic. These are like the two extremes settings of the relation between sparsity and dimension, Fourier dimension. So coming to Chang's lemma, what Chang's lemma says is you look at alpha such that f at alpha is greater than a certain threshold t. Let's call that one set collection support t, and RT is the dimension of the F2 span of support t. Okay. So RT is the quantity which you are interested in. Suppose if this threshold is t is 0 or very small, the support t will be entire support, and this RT will just be R. So Chang's lemma says that for every threshold t, it gives an upper bound on RT, and here is an upper bound in terms of the threshold t and the weight of the function f. Okay. So yeah, so in this work we consider these three interesting settings, which are k for t, which are k prime, and k double prime. These are the quantities which I defined earlier. For k is sparsity, k prime is max entropy, and k double prime is max rank entropy. So here are some other bounds which resemble Chang's lemma type bounds. So this is a bound by Swagato Sanyal. We showed that the rank is upper bounded by square root k log k. Again, another work by Chattopadhyay et al. They give another bound on rank, this time in terms of this k double prime and k. So what we show is we improve upon these bounds by Sanyal and Chattopadhyay et al. So we essentially show that we essentially throw in a delta term in the upper bound in both these bounds. So we show that rank is upper bound by square root k delta log k, and again rank is upper bound by delta k double prime log k. So yeah, so how do these bounds compare with respect to Chang's lemma? So if we plot delta versus k prime, here is a plot of delta versus k prime for a fixed r and k. So the red line is the red curve is the Chang's lemma, and the blue curve is the green one is our improvement to Sanyal, and the blue line is an observation which follows from Parshivag. So together with the red line, green line, and the blue curve, they subsume the Chang's lemma. And yeah, so natural question to ask is, are these bounds tight? So normally it's enough to show show a function for a particular setting of R and K. If you show a function which achieves this bound, it's but what we ask is something stronger. We say that given any R, K, K prime, and K double prime and delta, can you exhibit functions which match these bounds? For example, pictorially, what we ask is, are there functions on this green line and this blue curve for every at every point? I mean, given any delta and K prime, can we come up with a Boolean function which has weight delta and max entropy K prime? Okay. Yeah, the answer is yes. In most cases, and in one setting, it's up to log factors. So the functions which you obtain are obtained by taking the addressing function and replacing the target bits with functions on new variable. For example, one of our upper bounds is that given an R, K, K prime, and delta, such that R is square root K delta log K, is there a Boolean function which matches this, which has these parameters? And yeah, so we're doing this sort of a composition with the addressing function and we can obtain such a function. I mean, if you notice, there are these three parameters T, T prime, and A, and three independent parameters R, K, and K prime. So by setting this T, T prime, and A, you can make R, K, and K prime to whatever we want. Yeah, and yeah, that's it. So yeah, so this upper bounds on Fourier dimension, it has connections to one-way communication complexity of XOR functions. And an open question is that, so we considered these three thresholds, K, K prime, and K double prime. For all the three thresholds, RT turns out to be R. So the question is, can you consider other thresholds and show Chang-Sama type bounds for those thresholds? And as I pointed before, addressing function has rank T, rank T and sparsity roughly T square. Addressing function I've shown before that it has rank T plus log T and sparsity T square. So is there a function which is so the relation there is quadratic, but the bound showed by Swagato is that R is less than square root K log K. So do we know of a function which whose rank is greater than K? We know that it's less than square root K log K, and we know addressing has square root K, but is there a function which does better than addressing? That would be interesting to know. Yeah, that's all for now. Yeah.
Let's thank the speaker. Okay, so we have about a minute for some questions, but this is the last talk, so perhaps we can have a little longer time for questions. Okay, it doesn't look like there are any questions. I'm also monitoring the chat, none there. So it's worthwhile, before we sort of end the session, it's worthwhile reminding you that there are these talks, slightly longer versions are there on YouTube. So please have a look. If you have questions that come up, then please feel free to contact the authors directly. Also, they are around during the session, the rest of the session. So with that, I think I'll conclude this session's talk, and we'll take a brief pause until the next invited talk.
Yeah, I just want to remind everyone that Scott Aronson will be speaking at 7:30 which should be good. It's entertaining and inspiring usually. So please attend. Thank you.
And maybe I can also pitch in. There is the business meeting of IRX at 6 o'clock. Everybody is welcome to come and have your say.
Have your say. All right. Yeah. Thank you for that. Also, actually, I almost forgot. Thank you.
Thank you.